So we worked out the relationship between different matrices that represent a linear map relative to different bases. So now we can return to the original question that caused us to figure that out in the first place. And that question was this: if we have a linear map between finite dimensional vector spaces that would have to have the same dimension, can we sensibly define what the determinant of this linear map is? And our original idea was, well, why don't we just take a matrix that represents this linear map, take the determinant of that matrix, and call that the determinant of the linear map? Well, that leads us to a problem of having our determinant for H being well defined, because there are different matrices that represent the same linear map. So if we want to, define something that we are calling the determinant of H, it shouldn't depend on which representing matrix you choose. So that's why we had to work out the relationship between the different representing matrices. All right, so now that we know this relationship, let's test our idea for a definition for the determinant of a linear map by checking if different representing matrices have the same determinant. So here's the example that we worked out. We had this linear map from R2 to P1, right? This one here, and we were going to use the standard basis always on the domain side, and on the codomain side for P1, we had these two different bases, and we worked out the matrices that represent these two bases, or that represent this map relative to these two bases. It was these two. So now we can calculate the determinant of each of these and see if we get the same thing. Incidentally, this is how we figured out our second representing matrix. It was the product of the first representing matrix and this transition matrix. So let's calculate the determinant of this one. So it's -1 plus, so -3, sorry, minus -4, so -3 plus 4, so that's 1. And what about the second one? So the second one is going to be messier because the numbers are bigger. So -6 times -22 minus 32 times 4. So this is going to be 120, 132. And then 32 times 4 is 128. Right? Yes. Okay. So this comes out to 4. So these determinants did not come out to be the same, right? And that shouldn't really surprise us because, right, what we calculated right here, the second determinant, it was the determinant of this matrix. Well, we know that the determinant respects products. So the determinant of -22, 32, 4, -6, that's going to be the determinant of this transition matrix, 2 minus 12, 0, 2, times the determinant of our first representing matrix, 1 minus 2, 2 minus 3. Okay, this determinant of our first representing matrix, that was 1. And the determinant of this transition matrix is 2 times 2 minus 12 times 0, so 4. Right. So because this transition matrix came out to be kind of wild, its determinant doesn't have to be anything in particular, and so it changes the determinant of the representing matrix, right? So what this is showing us is there's no one correct representing matrix that we can use to define the determinant of a linear transformation. So in this general setting where you're going from one vector space to a different vector space, there's no sensible way to define the determinant of that linear map.